So hello guys, here we have question number 5 from Build Up Your Understanding exercise of the chapter Electrostatics from Pathfinder. First let's look at the question. Three identical point charges are placed on the vertices of an equilateral triangle. At how many places within the triangle electric field vanishes? So if you want to give it a try without the hint, you can do it now. If you want the hint, here it is. Think about its medians. So if you want to try it again, you can do it now. Now let's look at the solution. And first of all, I would like to say that a lot of this solution has been inspired from and taken from the AOPS user Mathsworm from his blog, and its link is in the description. So please check it out once. It's really awesome. Now let's look at the solution. So first of all, basically we have to find the neutral points on the triangle, and it's obvious that such a point can't lie outside the triangle ABC because the forces cannot be balanced in such a situation. So what I'm saying here is that if the point is somewhere outside the triangle, then all the forces due to this, and due to this will be in this direction, and no force will be balancing it in the opposite direction. So it obviously cannot be outside the triangle. So if we start directly analyzing for any general point, we might end up nowhere. So let's first try to see the obvious points where the electric field would be zero. So the first point in an equilateral triangle which comes to my mind is the centroid, or the orthocenter or the incenter, which is basically the same for an equilateral triangle. And it's obvious that the field here would be zero due to the symmetry. And now if we try to be slightly more general, let's see if we can find more such points on the median or altitude. To do this, first let's do a simple test of determining the directions of electric field on various points on the median. So without loss of generality, let's consider median AE here A, and this is E. So now along this line, as we know that H is one of the neutral points, which is the centroid. So first let's try looking around it. So if we move slightly below H, the repulsive force due to B and C will increase. This distance would tend to decrease, and while that from the A will decrease, so it's clearly experiencing an upward force in this region. So basically what I'm saying here is that if it comes slightly down, this distance increases and this distance decreases, so basically it experiences an upward force. So the direction of electric field is upward, as shown here in by the violet arrows. So now let's go slightly above from the point H, and we can see that the repulsive force due to A will increase, while that from the other two will decrease. So it will experience a force in the downward direction in this region. So by similar logic, the electric field in the upward, just the region just above H, it will be in the downward direction. And we can observe from here that if we keep on going towards A, the repulsive force from A will keep on increasing, and that from the other two it will keep on decreasing. So it's clear that we can't get a neutral point in the region AH. So we cannot get a neutral point in this region. And while this isn't the case, if we go down from H, as the repulsive force from A will keep on decreasing, but it isn't necessary that the net repulsive forces due to B and C will only increase, but it will increase till a certain extent and then it shall decrease, because as the particle comes down, this angle here, this is also increasing. So their component in the upward direction will also be decreasing to some extent due to that. And now from the above 2 points, we can conclude that we must get a neutral point between H and E for sure. So first let's try to find this point. So here I have assumed that let's consider the point which is at a distance x above point E, and I have assumed the height of the equilateral triangle to be h, and h will be L root 3 by 2 because this is an equilateral triangle. So at this point the electric fields we can write are kq square by L root 3 minus L root 3 by 2 minus x whole squared, which is the force due to A, should balance the vertical component due to these two charges, which will be twice of kq square by x square plus L square by 4 multiplied by cos of this angle, which will be x over this length, which will be x over root of x square plus L square by 4. And we get this equation, and on solving this will be very tedious manually. So just plotting a graph, we can see that we are getting two roots between 0 and 1, And on solving this equation, we get three real roots: two between 0 and 1, the only ones which concern us here, and one greater than 3, which we can eliminate clearly, because that we are not considering points outside the equilateral triangle. So we don't really need to solve for the roots, and here is a plot, and we can clearly see that one point corresponds to the centroid and another to the point between h and d, just as we predicted. So basically we got that there will be 2 points on each of the median, and one will be common in all three, so there will be 4 points. So this finally tells us that at least 4 points must exist in this triangle, one centroid and one another point on each of the three medians. Now the part after this isn't very trivial and comparatively harder to find unless we are looking for it. So basically, the part after we have to prove that there will be no such points other than these four in this whole equilateral triangle. We have to just guess this initially, and then we have to try to prove this, because it isn't very obvious to see. So the 4 points we found above are the only neutral points in the plane. So we have to now prove that there is no such other point exists. So our claim is that no such other points exist, and we have to prove it now. So first of all, to prove this, let's consider a general point P inside the triangle. This is the general point P. So now to prove this, we do a construction that we rotate the triangle by 60 degrees about point C, such that B maps to A and A maps to A1, which means that the point B comes to point A and point A comes to some point A1. And so now here I assume that the angles of a triangle APQ, this triangle, are alpha, beta and gamma at Q, P and A respectively. And as triangle CPQ is equilateral, this is equilateral because this length is equals to this length, and we have rotated by 60 degrees, so this angle should be 60 degree. So this triangle is an equilateral triangle. So and what we can get is triangle BPC is congruent to triangle AQC. We can see this by a similar logic, that this triangle is actually just being rotated to this triangle. So these two triangles are congruent. You can prove them using the values also. So what we can say from here, angle AQP, which is this angle AQP, it should be equals to 60 plus alpha, because this angle is 60 and this angle is alpha, so it should be 60 plus alpha. And as this triangle is congruent to this triangle, this angle should be equals to this. So what we get from here is that the other angle is BPC, so BPC should be equals to pi by 3 plus alpha. And on similar logics, we can get that angle CPA is pi by 3 plus beta, which is CPA, this angle. This angle is 60 and the other part is beta, so that should be 60 plus beta. And similarly, angle APB is pi by 3 plus gamma. Now here I was assumed the distances AP, BP and CP to be x, y, z respectively. So now the vector diagram of the forces at P can be shown as, so the forces here are the three violet arrows I have shown here. So the forces can be shown like this, and on slightly rearranging them, moving this vector in this direction and moving this vector in this direction slightly, we can get a triangle. And this is a triangle only in the case when the sum of the three forces should be 0. So now we can apply sine rule here. So that's what I've written here. So for neutral point, these forces should add up to 0, hence they should form a triangle as shown above. Then applying sine rule here, and this it also has a special name called as Lamy's theorem. You can look it up, and it's just basically the same thing as sine rule, and it's shown above how it does. So what we get from here is that kq by x square over sine of pi by 3 plus alpha equals to kq by y square upon sine of pi by 3 plus beta equals to kq by z square over sine of pi by 3 plus gamma. And on kq can be cancelled here, so x square sine pi by 3 plus alpha equals to y square sine pi by 3 plus beta equals to z square sine pi by 3 plus gamma. And by sine rule in triangle APQ, in this triangle, what we can get is x by sine alpha equals to y by sine beta equals to z by sine gamma. So writing that here, and substituting sine alpha in place of x, and the common factor will be cancelled. So we finally get that sine square alpha times sine of pi by 3 plus alpha, and similarly for beta and gamma, should be equal. So this is the condition which is required to be satisfied for a neutral point. So now to analyze if these alpha, beta and gamma wherever are possible, we consider the function sine square x times sine of pi by 3 plus x. So we can analyze this by directly differentiating it, or just by plotting the graph and analyzing the values. So I just plotted a graph. You can check it has been done by differentiating in the maths firm's blog, so do check it out. So here if we see that the value of alpha can be between 0 to alpha 0 to pi, sorry, and we can see that this function is a 2-1 function in any range, which means that for any value of y there can be only 2 values of x at most. So that's what I've said here, and from the graph we can see that the function is at most 2 to 1 in the range of 0 to pi, which implies that the three solutions alpha, beta and gamma, at least 2 of them should be equal. So basically we know that the function is equal for f of alpha equals to f of beta equals to f of gamma, and we know that it's a 2:1 function, so at least 2 of them should be equal. So here without loss of generality, let's assume that, let's say, alpha equals to gamma. So from here what we can say that these two lengths are equal, and this length is equals to this length. So basically these two lengths are equal, so that implies that the point should lie on the medians. So what we can say, so if any two of the three angles are equal, it's clear from the diagram that the point P should lie on any of the three medians. So this completes our solution, as we have already found the points on the medians, hence there will be 4 neutral points in this case. So basically we proved here that the for such a neutral point to exist, it should exist on the medians, and we had earlier calculated that there will be 4 such points on the medians. So there will be only 4 such points in total. Hope you all liked the video. Please leave a like, share and subscribe. Thank you.